Mathematical definition of dimensions. Now that we have studied those relations that our space itself bears within it, we can return to the questions, but what in reality do the dimensions of space represent? And why are there three of them? The fact that it is impossible to define three-dimensionality mathematically must appear strange. We are, however, little conscious of this, and it seems to us a paradox, because we speak of the dimensions of space. However, it remains a fact that mathematics does not sense the dimensions of space. The question then arises, how can such a fine instrument of analysis as mathematics not feel dimensions, if they represent some real properties of space? Speaking of mathematics, it is first necessary to recognize, as a fundamental premise, that correspondent to each mathematical expression is always the relation of some realities. If there were no such thing, if it were not to be true, then there is no mathematics. This is its principal essence and its principal content, for to express the correlations of magnitudes is the problem of mathematics. However, these correlations must be between something. Therefore, instead of the algebraical A, B, and C, it must be possible to substitute some reality. This is the ABC of all mathematics. A, B, and C are credit notes and can be good, only if behind them, there lies something real. They are rendered counterfeit, if behind them, there is no reality whatsoever. Dimensions, however, play a very strange role, as if we designate them by the algebraic symbols A, B, and C, then they possess the nature of counterfeit bills. For this particular A, B, and C, it is impossible to substitute any real magnitudes that are capable of expressing the correlations of dimensions. Usually dimensions are represented by powers, the first, the second and the third, that is, if a line is called A, then a square, the sides of which are equal to this line, is called A to the power of 2, and a cube, the face of which is equal to this square, is called A to the power of 3. This, among other things, gave Hinton the foundation upon which he constructed his theory of tesseracts, four-dimensional solids, i.e. A to the power of 4. This is, however, pure fantasy, because the representation of dimensions by powers is entirely conditional, as it is only possible to represent all powers on a line. For example, take the segment of a line equal to 5 mm. Then a segment equal to 25 mm will be the square of it, i.e. A to the power of 2, and a segment of 125 mm will be the cube, A to the power of 3. How can we understand, then, that mathematics does not feel dimensions, that it is impossible to express mathematically the differences between dimensions? It is possible to understand and explain this because of one thing only, namely that this difference does not exist. We know in reality that all three dimensions are in substance identical, that it is not possible to regard each of the three dimensions as following a sequence. The first, the second and the third, or the other way around. This alone proves that dimensions are not mathematical magnitudes. All the real properties of a thing can be expressed mathematically as quantities, i.e. as numbers, showing the relation of these properties to other properties. However, in the matter of dimensions, it is as if mathematics sees more than we do, or farther than we do. Through some boundaries that arrest us, but not it, and sees that no realities correspond to our concepts of dimension. If the three dimensions really corresponded to three powers, then we would have the right to say that only these three powers refer to geometry, and that all the other higher powers, beginning with the fourth, lie beyond geometry. However, even this is denied to us, and the representation of dimensions by powers remains arbitrary. More correctly speaking, geometry, from the standpoint of mathematics, is an artificial system for the solving of problems based upon conditional data, deduced probably from the properties of our psyche. The system for the investigation of higher space, Hinton calls metageometry, and with metageometry he connects the names of Lobachevsky and Gauss, among other investigators of non-Euclidean geometry. We can now consider in what relation the questions touched upon by us stand to the theories of these scientists. Hinton deduces his ideas from Kant and Lobachevsky. Others, on the contrary, place Kant's ideas in opposition to those of Lobachevsky. Thus, Roberto Bonola, in Non-Euclidean Geometry, declares that Lobachevsky's concept of space is contrary to that of Kant. He says, Kantian doctrine considered space as a subjective intuition, a necessary presupposition of every experience. Lobachevsky's doctrine was rather allied to sensualism and the current empiricism, compelling geometry to take its place among the experienced sciences. Roberto Bonola, Non-Euclidean Geometry, The Open Court Publishing Company, Chicago, 1912, pages 92 and 93. Which of these views is true, and in what relation do Lobachevsky's ideas stand to our problem? The correct answer to this question is, in no relation. Non-Euclidean geometry is not metageometry, and non-Euclidean geometry stands in the same relation to metageometry and Euclidean geometry itself. The results of non-Euclidean geometry, which have submitted the fundamental axioms of Euclid to a revaluation, find their most complete expression in the works of Bolyai, Gauss and Lobachevsky, embracing the following formula: the axioms of a given geometry express the properties of a given space. Thus geometry on the plane accepts all three Euclidean axioms, i.e. a straight line is the shortest distance between 2 points. Any figure may be transferred into another position without changing its properties. Parallel lines do not meet. This last axiom is formulated differently by Euclid. In the geometry of a sphere, or on a concave surface, the first two axioms alone are true, because the meridians, which are separated at the equator, meet at the poles. In geometry upon the surface of irregular curvatures, only the first axiom is true. The second, regarding the transference of figures, is impossible, because the figures taken in one part of an irregular surface can change when transferred into another place. Also, the sum of the angles of a triangle can be either more or less than two right angles. Therefore, axioms express the difference of properties of various kinds of surfaces. A geometrical axiom is a law of a given surface. But what is a surface? Lobachevsky's merit lies in the fact that he found it necessary to revise the fundamental concepts of geometry. However, he never went so far as to revalue these concepts from Kant's standpoint. At the same time, he is in no sense contradicting Kant. A surface, in the mind of Lobachevsky as a geometrician, was only a means for the generalization of certain properties, upon which this or that geometrical system was constructed, or the generalization of the properties of certain given lines. About the reality or the unreality of a surface he never postulated. Thus, on the one hand, Bonola, who ascribed to Lobachevsky views opposing Kant's, and their proximity to sensualism, along with current empiricism, is quite wrong. While on the other hand, it is not impossible either to conceive that Hinton subjectively ascribed to Gauss and Lobachevsky the inauguration of a new era in philosophy. Non-Euclidean geometry, including that of Lobachevsky, has no relation to metageometry whatsoever. Lobachevsky does not go outside of the three-dimensional sphere. Metageometry regards the three-dimensional sphere as a section of a higher space. Among mathematicians, Riemann, who understood the relation of time to space, was closest of all to this idea. The point of three-dimensional space is a section of a metageometrical line. It is impossible to generalize on any surface the lines considered in metageometry. Perhaps this last statement is the most important for the definition of the difference between geometries, Euclidean, non-Euclidean and metageometry. It is impossible to regard metageometrical lines as distances between points in our space, and it is impossible also to represent them as forming figures in our space. The consideration of the possible properties of lines lying outside of our space, the relation of these lines and their angle to the lines, surfaces and solids of our geometry, form the subject matter of metageometry. The investigators of non-Euclidean geometry could not bring themselves to reject the consideration of surfaces. There is something almost tragic in this. See what surfaces Beltrami invented in his investigation of non-Euclidean geometry. One of his surfaces resembles the surface of a ventilator, another the inner surface of a funnel. However, he could not reconcile himself to reject the surface, to cast it aside for once and for all, imagining that the line can be independent of a surface, i.e. a series of lines that are parallel or nearly parallel cannot be generalized on any surface, or even in three-dimensional space. Because of this, both he and many other geometers developing non-Euclidean geometry could not transcend the three-dimensional world. Mechanics recognizes the line in time, i.e. such a line as it is impossible by any means to imagine upon the surface, or as the distance between 2 points of space. This line is taken into consideration in calculations pertaining to machines. However, geometry never touched this line and dealt always with its sections only. Now therefore it is possible to return to the question, what is space? The answer should be an exact definition and explanation of the three-dimensionality of space as a property of the world. However, this is not possible. The three-dimensionality of space, as an objective phenomenon, remains just as enigmatic and inconceivable as it was before. In relation to three-dimensionality, it is necessary either to accept it as a thing given, and to add this to the two data that we established in the beginning, or to recognize the fallacy of all objective methods of reasoning, and return to another method, outlined in the beginning of this commentary. Then on the basis of the two fundamental data that we started out with, i.e. the world and consciousness, it is necessary to establish whether three-dimensional space is a property of the world, or a property of our knowledge of the world. Beginning with Kant, who affirms that space is a property of the receptivity of the world by our consciousness, we intentionally deviated far from this statement and regarded space as a property of the world. Along with Hinton, it was postulated whether our space itself bears within it relations which permit us to establish its relations to higher space. Then on the basis of that postulate was built a whole series of analogies, which somewhat clarified for us the problem of space and time in their mutual correlations, but which, as was stated, did not explain anything concerning the principal question of the causes of the three-dimensionality of space. The method of analogies is, generally speaking, a rather tormenting thing, as with it, you walk in a vicious circle. It helps to elucidate certain thing and the relation of certain things, but in substance it never gives a direct answer to anything. After several lengthy attempts to analyze complex problems with the aid of analogies, you feel the futility of all effort, you feel you are walking alongside a solid wall. Thereupon you begin to experience a hatred and aversion for all analogies and find it necessary to search in the most direct way possible, which leads to where you would like to go. The problem of higher dimensions has usually been analyzed by the method of analogies, and only more recently has science begun to elaborate that direct method, which will be shown further on in this discourse. If we desire to go straight, without deviating, then we shall keep strictly to the fundamental propositions of Kant. However, if we were to formulate Hinton's thoughts from the point of view of these propositions, then it would be as follows. We bear within ourselves the conditions of our space, and therefore within ourselves we shall find the conditions that will permit us to establish correlations between our space and higher space. In other words, we shall find the conditions of the three-dimensionality of the world in our psyche, in our own receptive apparatus, and shall find exactly there the conditions of the possibility of the higher dimensional world. Propounding the problem in this way, we place ourselves upon a direct path, and should receive an answer to the question, what is space and its three-dimensionality? How then can we seek the solution? Plainly by studying our consciousness and its properties. We should free ourselves from all analogies, entering the correct and direct path toward a resolution of the fundamental question about the objectivity or subjectivity of space. If we resolve to study the psychic forms by which we perceive the world, discovering then, if there might not exist a correspondence between them and the three-dimensionality of the world. That is, if the three-dimensional extension of space, with its properties, does not result from the properties of the psyche that are known to us.